Hey everyone, I'm Nick, and in this episode of This Week in Architecture, we're going to be going over a paper called Crash Consistency in Encrypted Non-Volatile Main Memory Systems. So this is from HPCA 2018. It's a pretty interesting paper. So we'll go over what crash consistency means, and then how this relates to encryption and then non-volatile memory. So let's go ahead and get started. So we'll be using a presentation from the actual conference. Okay, so a little bit of background on non-volatile memory. So we like it for a number of reasons, right? It's high speed, durable, and byte addressable. Just a little background on NVM. So when we say high speed, it's high speed with respect to most durable storage. So something like a disk that doesn't lose the data when we turn the power off, right? It's still a bit slower than something like DRAM by around 4x or so. And there's two things that we want out of NVM, right? And especially in the context of this paper. So one thing that we like to have is this thing called crash consistency on systems with non-volatile memory, right? So what is crash consistency? Well, at a very high level, think about if you've got some giant simulation that takes, say, a month to run. Well, what happens if, half a month in, something goes wrong with, say, part of the, part of your cluster, right, and you lose power? Well, do you have to completely restart the entire application again, right? This is one of those things where we don't want to, say, spend another 14 days or 20 days like rerunning the same program. So if we can have something like non-volatile main memory, where the data is going to be persistent on a power failure, what we'd like to have is this thing called crash consistency. Basically meaning that we're in a consistent state if we say the program crashes based on some maybe power failure that we can recover from. Then we might have to pay a little bit of a cost to do that recovery. But overall, right, it can save us a whole lot of time, especially if we don't have to, say, restart an entire application. And the other thing is encryption. So we're talking about, now we've got a new kind of surface area for attack here. So normal stick of DRAM, if you unplug it, you lose all the data. But now think about it more in terms of, what happens if you've got a stick of, non-volatile memory, so like the one in the picture. Well, if we unplug that, we don't actually lose the data, right? We don't lose the data because it's non-volatile. So now we've got this other kind of, potential security problem. So let's first talk about crash consistency and get a better idea of what this means. So let's we'll use this idea of a linked list. So we've got some linked list in memory. We've got a pointer to the head of the linked list, and then we have nodes, each of which points to the next node in the linked list. And let's say we want to add a new node, and when it's shaded dark blue, it means it's persistent in non-volatile memory, right? So that means if we lose power, we still have that data. So let's say we create a new node, right? So we're adding a new node that's going to be the new head of the linked list. So we create the new node, but this is going to be in the cache, right? So it's only going to become persistent if we write it all the way back to non-volatile memory. And let's say the next thing we do is we switch the head pointer, right? And the thing to note here is this dark blue means that it's persistent in non-volatile memory. And this can happen for a number of reasons. Maybe we're actively modifying maybe this new node in the linked list, and then maybe based on a cache eviction policies, maybe just the head of the linked list or the head pointer gets flushed out to non-volatile memory before the node does, right? There could be a number of circumstances that cause this, but the key problem here is that what happens if we have a power failure? Well, now because the actual data, right, the node itself for the linked list was never actually flushed to non-volatile memory. Now I have a head pointer that's essentially pointing to the middle of nowhere, right? It doesn't point to any actual valid piece of data. But this is even worse than that because now we've lost our entire linked list because we were relying on the fact that this node in the linked list that we just lost points to the original head of the linked list. See with this arrow. So now we've got a head pointer that points to the middle of nowhere. We've completely lost our linked list, so we can't actually recover from this. So what we'd like to have happen is something like this. So this is a very simple way to solve this problem. So you go ahead and you've got your original linked list. You add a new node, right? But the thing is, before you switch the head pointer, you make the node persistent or durable in non-volatile memory. So you flush it to non-volatile memory before you switch the head pointer, right? That makes sure that at any point during this process, you can recover. So if, let's say, during this stage, right before we switch the head pointer, and maybe while the new node is not in non-volatile memory, if we crash, we're still fine because the head pointer just points to the original node. Then after we switch the head, right, we've already guaranteed before that the node is persistent in non-volatile memory. So it's okay if an error, if a crash happens here, right, because we've got a state that we can recover from. That's what we mean by crash consistent. And there's been a number of libraries that have shown very kind of a software approach to solving this. So the actual implementation that you would use to solve this problem, you can think of it as very simply as, okay, we need to flush cache lines, and then we need to make sure that they've been written back by that point. So typically the way this, if the lowest level is implemented is using something like a CL flush instruction. So that's a cache line flush instruction. And then you'd follow that with the fence instruction. And all the fence instruction says is it guarantees that once the fence instruction happens, all the previous, say, cache line flushes have occurred. So we've already flushed everything out to our non-volatile memory, right? So that's kind of at a very low level what's going on there. So non-volatile memory is durable, right? And again, this introduces a new error. So what if I'm storing, usernames and passwords, or any kind of data that's sensitive on my non-volatile memory? Well, there's a security problem here with, if there's an attacker, right? So they could have physical access to the machine. So we might not want to, just have normal data being stored in our non-volatile memory, right? We might want some extra protection, so we'd use something like encryption. So instead of storing the actual data, right, we're storing encrypted data on our non-volatile memory, right? So let's go a little bit into kind of the motivation for this paper. What if we have a crash in a system that's using non-volatile memory? What happens? Are we in a state that's crash consistent? And the answer is actually no, really. At the time of this work, the main idea behind this paper was that you're not guaranteed to have crash consistency in encrypted NVM systems, right? So that's what this paper really targets. They want to provide crash consistency for this type of system. And of course, it has to be low overhead, right? We're already talking about something that takes a little bit of overhead, guaranteeing some kind of recoverability. But what we want to make sure is that it's not excessive overhead. So a little background on encryption. So there's a number of ways that you can encrypt and decrypt data. So a very basic way is you just encrypt the data directly with the key. So you've got, say, some read access, and then every time you do a read access, you have to decrypt the data, right? Because this read is reading from the encrypted data that's in non-volatile memory, and then we're having to decrypt it. Once we're on chip in the caches, everything is normal plain text, right? It's not encrypted. And that's because it'd be really hard, or if not impossible, to actually for someone with physical access to, say, try to read something that's, say, in the caches versus being able to pop out a stick of non-volatile memory. So here we've got this read access, we're decrypting, and then we get the plain text out, which is just the normal data, non-encrypted. But this is kind of bad, right? It's bad because now every time we do a read, we have to do this decryption, right? And this decryption can only happen after the read. So this is pretty bad, right? And especially because it's on the critical path. And when we say critical path, what we mean is I'm doing something that I have to pay that price no matter what, and it's going to back up things later on. So if I'm reading something, I'm going to be using that data. So we typically say that reads are going to be on the critical path. But with something like a write isn't necessarily on the critical path. Typically, when we're writing something, we don't immediately read what we just wrote. So we don't usually say that writes are on the critical path, unless there's some other circumstances, which we'll go into a little bit here. So how do we actually get rid of this problem of having our decryption happen right after our read, right? Can we paralyze this at all? And there's this interesting paper. So this paper is from 1979. It's on cryptography. It introduced this counter mode encryption, or at least spoke about this counter mode encryption. So instead of directly encrypting the data, what you end up doing is you encrypt a unique counter for each cache line. And this encryption happens at each write. So basically there's a timestamp of a counter, and you encrypt a cache line's write, right, with a particular counter value. So you need to be able to save that counter value and then the cache line. So how does this, really work? You've got some counter that gets generated and it goes into this encryption engine. And this encryption engine generates this thing called a one-time padding, or OTP. So outside of that, that's what this encrypted bit string is. It's this OTP. And then what happens is, say, on a write, right, from your processor to your last level cache. So from your last level cache, you're writing back to non-volatile memory. So instead of having to directly encrypt this data, right, we can basically just go ahead and encrypt this counter on the side, and then we can just XOR the plain text with whatever the encrypted bit string is, right? And then that gets saved to the encrypted memory. So now an attacker can't just pull out, stick a NVM and read everything because it's encrypted. But we also don't have to wait for the data to come all the way from the last level cache in order to encrypt it, right, before the write. But there's a little bit of a problem here, which is, where is this counter coming from? Right, so like I said earlier, whenever we're doing these counter has to be stored someplace, right? And we need a unique counter value for every cache line. So typically, a naive solution, you just keep this in non-volatile memory, but that means you have to access non-volatile memory before you can start the encryption. So they introduce, or there's been papers in the past that have used a counter cache. So basically, just like you store data in a cache, you store counter values in a cache as well. Right, that way, whenever there's going to be a write occurring, you can go ahead and fetch from the counter cache instead of accessing non-volatile memory. You can go ahead and begin this encryption engine process, right, of generating this one-time padding, and then it's a pretty cheap operation of this XOR, right? XORs will be a cheap operation. It's not going to put a whole lot of stress, and then the decryption. When I say stress, it's not going to take a whole bunch of time. And then the process is kind of just reversed for a read. A read does a similar thing where we have to get a counter value, and then we generate that one-time padding, and while the data is being fetched from encrypted memory, right, we can generate this encrypted bit string. The data comes back from non-volatile memory. We XOR it, and then we have our original data back, right? And that gets sent into the cache hierarchy of our processor. That's a little bit on this process. And the key idea is we're shifting the decryption to be off the critical path. So on a read, we no longer have to wait until after the read to decrypt the data. We can basically use those counters, right? And we can decrypt based on those counters, and all we have to pay the price of is this XOR operation, which will be cheap. So we parallelize this, ends up with a shorter latency. It's good things. It's what we like to do. So let's talk about a write access now. So now this means two things. So if we just store the encrypted data, that's fine. We just have to worry about, okay, let's write just the data to the encrypted NVM. But now, because we're doing counter mode encryption, we have two things. So we have to write the data, but we also need to write the counter value. And the reason why we need this counter value is because, like we just showed, we need this counter value to decrypt the data, right? So this counter value is used to generate this one-time padding that's XORed with the data, right? Everything can't fit always in the counter cache. So eventually it will have to become persistent, right? Because the counter cache, when we lose power, we lose that as well. So we need to retain those counter values inside of something durable like non-volatile memory. So we need to save both. Now, what's the problem with this? So this is where the inconsistency comes up, and where we lose this nice property of being crash consistent. So if we write the data, but if something goes wrong when we write the counter, we can't actually recover from this. And the reason why we can't recover is because the counter is what's used to generate the one-time padding. If we don't have the right counter value, we can't decrypt the data. And likewise, so we're inconsistent, and so we can't recover. Likewise, if we write the counter, but something goes wrong with the data, right? Another issue here, right? Now we've basically written a counter, but we lost the data. So in both cases, we're led to this inconsistent state, so we can't recover from this. So the main goal of this paper is, first they showed that the problem was that a program can fail to recover if extending the current crash consistency mechanism to encrypted NVM. So you can't just plug and play existing crash consistency mechanisms when you're working with encrypted data. And then the goal of this is to extend crash consistency to support this, but very key aspect of this, a practical NVM system. So you can make some impractical changes that trivially solve this problem, but nobody would ever implement it, so it's not really a good solution. And they kind of go over that. But the main problem is that we need this data and this counter to be written back at the same time. We need either both of them to be written back or neither of them, right? Otherwise, we could lead to an inconsistent state where we don't have the data, right? Or we can't get the data back, rather. And so this would ensure us the consistency that we're looking for. But it doesn't necessarily have to be exactly at the same time. So, at a high level point of view, we can think of the data and counter being written back together at the exact same moment. But, one thing that we like to think of as this kind of as-if rule. So it's okay if they're not written back at the exact same time. If under all circumstances, it's as if they were written back at the same time. So let's talk about counter atomicity now, which is basically where we ensure the data and the associated counter reach NVM atomically. Right. So basically, this requires the data and the associated counter of a write access reach NVM atomically. Right. So that's counter atomicity. And then a counter-atomic write is a write that satisfies counter-atomicity, right? Just a couple of definitions there. So how do you ensure this? Well, you could go with a very impractical solution, which is you extend the last level cache with an extra 8 bytes, right? These 8 bytes are your counter, and then you have a 72-bit bus instead for writing things back, so you can write everything back together. So you get guaranteed counter-atomicity, right? So if you extend the memory system, in order to make sure you can write both the data and the counter back together, right? Yeah, you can of course guarantee counter atomicity. Now the big problem here is that nobody would ever implement it. Right? This is just something that would be, it's so crazy of an idea in terms of everyone would have to change, their last level caches and then also the memory interface. It's just not a practical solution, right? So how do you enforce it with the current memory interface, right? So we've got the 64-bit bus, so we can't write back 72-byte cache line in a single transaction, right? It would have to be they'd have to be written back separately, and also because our last level cache lines are 64 bytes, which means our counters are on different cache lines than our data. So we want to use this 64-bit bus, and very kind of simple solution. You just have the memory controller track the completion of data and counter writes and blocks dependent writes. So if there's a dependent write, you say, hey, you have to wait. And then we just have to track inside the memory controller the write back of both the counter and the data, right? And we're exploiting a fact in here. This is this thing called Intel ADR, which stands for asynchronous DRAM refresh. Very confusing name in terms of what it actually does. But at a very high level, you can think of it as a battery. Right? You can think of it as a battery for the memory controller that guarantees, hey, if something made it all the way down to the memory controller, I can make sure that whatever's in here, because I have some extra power in a battery, gets written back, right, to non-volatile memory. So as long as the memory controller can track, okay, I've got the data and I've got the counter in the memory controller, I can write both back, right? That's a guarantee that we need to make. And so the memory controller just needs to track that. But the problem here is that not only do we have extra counter writes, but we also have blocking, right? So now we have to block previous writes, right, in order to have this guarantee, at least in a very simple case. So, right, so we have this write access, write data, and write counter, and again we have 2 writes now. So it maintains a current memory system, but again, 2 writes, right? A write for the data, write for the counter, isn't great. So the other thing is the serialization that we mentioned briefly. So if I want to counter-atomically write something, and let's say these writes are dependent on each other, well, I can write the first thing, and so this is the write and the data and the counter. So I can write the data and then the counter, right? Again, these have to be 2 different transactions. And then I can write the data and the counter for the next one, and the counter, then the data for the next one. But again, these are all serialized. So that's kind of the worst case. But in a better case, what we'd like to have is all of these nice optimizations like reordering, coalescing, and buffering going on That way we can remove, say, writes to the same location. We can reorder writes. We can buffer them, all things that we can do in order to greatly improve performance, right? So we can save a whole bunch of time here, like this green block kind of implies. But there's a problem with this, right? The problem is with counter-atomicity, right? So this fundamentally breaks this idea that we just introduced called counter-atomicity. So how do we actually overcome that, right? So how do we overcome the fact that we've got twice the write traffic and we're blocking dependent writes? So this kind of naive case where we've got twice the traffic and we block dependent writes, they call this full counter-atomicity. Basically, all writes all writes are counter-atomic, and so they have to block dependent writes, and we still have this 2x write traffic. So the key observation here is that not all writes have to be counter-atomic, right? So all writes can be counter-atomic in terms of, okay, it's an easy way to just guarantee this solution, but it's not very practical in terms of performance. And so let's think about it in terms of how we actually recover in these crash consistency mechanisms. So typically we use a mechanism like redo or undo logging, journaling, also known as shadow paging, copy on write, which is also known as write-ahead logging, I believe. And the characteristics of these, we basically maintain multiple copies of data for crash consistency. So it's not necessarily a full duplicate of all your data, but whatever you're currently working on or the data you're currently modifying, you keep a backup of it, and then you've got your original data. And at any given moment, you're only modifying one of these. So if something bad goes on, right, you can recover. So if you're modifying the original, you have the backup data to recover from. And then if you're modifying the backup, well, you guarantee that the original is still consistent. So you always have one copy around. So let's look at this from an undo logging point of view. And first, a little bit of background. We've got these blue bars, which mean persist barriers. And then you have an undo logging transaction, which will compose of 3 steps: a prepare, a mutate, and a commit. And we'll go over what those mean. But these persist barriers, that's kind of what I talked about earlier as far as a cache line flush plus a barrier. So basically at the point of this blue bar right here, this is basically your memory fence. So you guarantee that all your data that you've been working with has been flushed to the memory system, and that barrier has completed, so you guarantee that everything has been written back. So let's look at modifying this original data structure. So we want to update, say, B in this. So first thing we do is in this prepare stage, we make a log and we back up the data. So this is with undo logging. So what we do is we go ahead and write B, but the problem at this point is that we're inconsistent. So B might still be in the caches, but the original data structure is fine. So if something goes wrong here, we can just recover from the original data structure and just discard the log. But then after this blue barrier, the undo log becomes persistent, so we're okay. The next thing is we want to actually mutate the data structure. So we want to make some update. So we update B to K, but now the original data structure is consistent. This K might be inside of the caches while the original data structure out in memory, right? It still shows B. So we've got this inconsistent state here. Now, we can still recover from this though, because we already created a log, right? So if something bad goes wrong here, we can go ahead and just look at the log and say, hey, recover from this point. And the last thing we have is this commit stage where we invalidate the undo log entry. Now this is where things get a little bit trickier, because now we're doing something that deals with both the log and the original data structure. So we're basically saying I want to discard this data structure that I'm pointing to, and I want to use the original data structure as the recovery point, right? So let's think about which part of data is consistent at each step of this transaction. So in the prepare stage, the backup is of course not consistent because it could be in the caches, but we haven't touched the data yet, right? We're just creating a backup, so we're fine. After that stage, right, the backup's going to be consistent, so we've got that barrier, that fence. We've made sure that the log is persisted, but now we're modifying the data in place, so that's not going to be consistent. But in the commit stage, right, that's where things get a little bit trickier, right? So when do we actually need counter-atomicity here? Well, we don't need it in the first stage because we have something that's persistent already that we can recover from. So this data is both persistent and it's in a consistent state that we can recover from it. And the mutate stage, the backup is, or undo log, but we need it for this commit stage, or basically finalizing these transactions. So the key point here is only the actual commit stage needs to be counter-atomic. So that's the only thing that really needs to pay this price for, the serialization. All these other stages can have all of our nice buffering and reordering and coalescing optimizations. So writes that do not immediately affect crash consistency do not need counter-atomicity, because we can do all kinds of messy things in terms of, or maybe not messy, but all kinds of clever things as far as optimizing our writes during the backup stage. But it's okay if something goes wrong while we're doing all those optimizations because the data hasn't been modified yet. Same thing in the mutate stage, but with the backup now, and so only the commit stage needs this guarantee. So they introduced this idea of selective counter-atomicity, basically only enforcing counter-atomicity for writes that immediately affect the consistency state. Okay, so let's talk a little bit about the software and the hardware support. So for the software, we've got a program, and the program has to be annotated for selective counter-atomicity. Basically, we need to tell, there has to be some way to denote which are the things that when written need to be counter-atomic. So then we have our annotated code and we compile this. So let's talk about these annotations. And basically we extend two things here. One of them is counter-atomic variables. This is how we say this thing needs to be written back counter-atomically. So any variable that directly affects consistency state needs to be a counter-atomic one. And the second thing is this counter cache write back. So I already said a little bit about having a cache line flush instruction and then a fence instruction. This is kind of similar to the cache line flush, but it's just for the counter cache, right? So we need to be able to make sure, these caches, right? The counter cache, just like the data cache, is not going to be, persistent. So we need to make sure we write back the counters that are inside the cache that correspond to a counter atomic write. So it's similar again to a data cache write back. Right, so we can think about where these things apply in terms of our transaction. So in the prepare stage, we need to make sure that after the prepare, when we've written our data logs, we need to also not only flush our data logs, but we need to flush the counter cache associated with the data logs. In the mutate stage, we need to do a similar thing, but we need to flush the counter cache for in-place updates. And then in commit, this is where we have our counter-atomic variable. So we update the validity counter-atomically. Right? We update the validity of, say, of the log. So we're saying the log is no longer valid. And then we have these persist barriers in between. So after this persist barrier, same kind of semantics in terms of the counter cache is guaranteed to have been written back to non-volatile memory by the time this persist barrier finishes. All right, so that's the software. So pretty minimal, just two things. But again, a little bit more burden on the programmer. They've got to know what variables in their code have to be counter-atomic, and then making sure to call this counter cache right back. The next thing is the actual hardware side. So we've got your processor, whether or not it's a read or write, or it's a counter-atomic read or write, or rather a counter-atomic write. And then we've got our memory controller, and then our data and a counter into our NVM that has encrypted data, and we're retaining the 64-bit bus. So let's talk a little bit about the memory controller, because this is where the hardware modifications are going. So inside of here, we've got our last level cache. And again, we've got this encryption engine off to the side with the counter cache. That way we can speed up on, say, a read. We can parallelize the encryption engine, starting generating that one-time padding, while over here, the NVM coordinator, right, while we're accessing our data in our encrypted NVM. So here we've got two different queues now to handle during a counter-atomic write. Right, so we've got our counter write queue and our data write queue, because we have to remember, right, when we're doing a write, we've got data coming from two different places, one of them coming from the last level cache, the other coming from the counter cache. And we need to be able to tell if we have the counter that needs to be written back now and the data that needs to be written back now. So we need to be able to compare if, the corresponding counter to the data are both in their respective queues. So let's look at this with a simple example. So counters come from the counter cache, Our data comes from our last level cache after it's encrypted through this encryption engine, through that process that we talked about earlier, through that one-time padding in XOR. And then again, we've got this Intel ADR here, right? So this Intel ADR, like we mentioned earlier, it's basically just a battery, and they're just extending this Intel ADR to encompass the scope of these small write queues, or relatively small write queues inside the memory controller, basically guaranteeing that if something has made it all the way to these queues, they're guaranteed to be written back. Okay, so let's look at it with a simple example. So say we want to have a counter atomic write. We need to wait until the ready bit is set in both the counter queue and the data queue, right? Why do we need to guarantee this? Well, we can't start a write on the data unless we know the counter is going to be written back. If the counter is not in the queue, but the data is, if we just wrote back the data, there's a chance that the counter is never written back, so we can't actually unencrypt it, or decrypt it rather. So we need to make sure they both make it into this queue before we start any writes. So let's say we're writing to address 0x100. The data comes in, but of course the ready bit's going to be set to 0 because it's not ready to be written back yet because we don't have the counter. Then eventually the counter comes in, both get set to 1, and they're ready to be flushed out, written to encrypted NVM. The other thing to kind of know here is that all the other data that's being, say, written, automatically the ready bit will be set to 1. And the reason being is the only thing we need to keep track of in terms of making sure that the data isn't written back before the counter, or the counter isn't written back before the data. We only care about the counter atomic variables. Everything else that's not counter atomic, we can before all our nice optimizations are. So we don't have to wait on a write to do something with a non-counter atomic write. So what about a failure? Well, again, this Intel ADR, we're making sure that everything in this counters, if the ready bits are set to 1, get written back. If something doesn't have a ready bit set to 1, it's not going to be written back. They just get kind of kicked out. All right. So in their evaluation, x86 out of order, counter cache is a megabyte, and then 8 gigs of PCM. Encryption latency 40 nanoseconds. Right, and they compare against a number of designs. So first of all is a no encryption design, so kind of a baseline. Then they have an ideal design without counter atomicity overhead. Then they show what would happen. Well, what if you did to the extreme and you extended the bus to be 72-byte cache lines with a 72-bit bus? What happens if you do full counter atomicity? So that's if every write is a counter atomic write. And then their actual proposal, which is this selective counter atomicity. And they do it on a number of different apps representing modifying different data structures. So let's talk about throughput first. So this is the average throughput normalized to single core, no encryption, right? So basically as fast as you could. Average throughput normalized to single core, no encryption. So compared to SCA and FCA, so SCA is their proposal, FCA is the full counter atomic one. It's 40% faster, right? 40% faster than FCA, so significant improvement into doing the naive solution. And then even compared to the extended bus, where we do the, unlikely to ever happen, make the memory interface 72 bits and extend the cache lines to 72 bytes, it's only about 10% slower. So it's pretty good compared to a drastic solution. And again, a lot of this is probably because it has a wider memory bus, right? So again, this is throughput. All right, so then we've got a variable transaction size. So here we've got average runtime of SCA, normalized to ideal design, and the number of cache lines are getting modified here in a transaction. So only for a single cache line being modified here, just one, it's only about 7.7% overhead, right? Normalized to this ideal design without any overhead. And then in the best case of 64 bytes, or rather 64 cache lines being modified, the overhead's pretty much completely gone. But this kind of makes sense. The reason why it makes sense is because we only really pay a penalty if there's a counter-atomic write. So if most of our work is not counter-atomic writes, we still get all the nice optimizations, and we only pay that price once. And if we do a whole bunch of writes and only one counter-atomic one, it's almost like we didn't do really any counter-atomic writes. We basically had all this space to do optimizations. We only had maybe a slight difference, so pretty much negligible. All right, so in summary, existing crash consistency mechanisms are not intended to support encrypted NVM systems. The contribution is this counter-atomicity idea and atomic selective counter-atomicity, right? And this reduces the counter-atomicity overhead of just kind of a naive implementation, while also keeping the existing memory interface. Basically, all they do is they track inside the memory controller. That allows them to maintain the existing memory interface and small extension to ADR, and a little bit of programmer overhead as well. And again, 40% faster than a naive solution. And again, selective versus ideal, less than 7.7% overhead, very low overhead. Right, so that was this paper, Crash Consistency in Encrypted Non-Volatile Main Memory Systems. So I thought it was pretty interesting. I felt like sharing it. If you're interested in this paper, I'll go ahead and link it below as well. If you're interested in any of my other series on, say, programming, I've got everything here at github.com/coffeebeforearch. So this is my GitHub page where I host all the code for all my series. So we've got stuff on C++ programming, GPU programming with CUDA, high-performance C++ programming, and a whole bunch of other stuff. But that's going to go ahead and do it for today. As always, I'm Nick, and I hope you have a nice day.